In this video, I want to take a look at a way of visualizing functions of a complex variable using color. So here's what I'm going to do. So I have right here in front of me a complex plane. So the real axis runs through the middle horizontally, the imaginary axis runs through the middle vertically. So 0 is right there at the origin. And what I'm going to do, what I have done, is I'm colored every point in the plane with a color. So, for instance, numbers along the positive real axis are shades of yellow. 1 is a nice bright yellow. As I move further away from 0, the shade gets lighter, and as I move closer to 0, the shade gets darker. Negative reals are shades of blue. Positive imaginaries are this, well, I don't know, pinkish color up there. And negative imaginaries are this green down here. Again, the further you get away from 0, the lighter the shade. The closer to 0, the darker the shade. 0 itself is black. So I can show you the color of different numbers by just typing them in here, right? So if I say 0, every point on that plane is now being colored by the color of 0, and that all looks black. If I say 1, then everything is being colored by the color of 1. Right? Notice there's 1, here's 2, a little bit lighter, here's 3, a little bit lighter, and in any direction again I said in any direction you get lighter as you move away. Here's I, and here's minus I, and here's minus 1. Is that blue? Okay. When I say that this is equal to X, then every point is being colored by its own color, right? You take whatever the value is, you say, oh, at this point, I want the color of this point, and at this point, I want the color of this point. And so everything's being colored by itself. Notice that you have this rainbow color wheel going all the way around. And just, I don't know if it's just an optical illusion or something, but you can really see the unit circle in there with that brightness of color right through this. Right. So I'm plotting here from -2 to +2 in both directions. So 1 is right there, 0, -1, I, minus I. Okay. Now, I can look at other functions, like what happens if I do x squared? Well, what do I see here? One is I see it looks like the color wheel goes around twice, but I see in the real direction, both on the positive side and the negative side, I'm seeing the color yellow. But that makes some sense because whether I plug in a positive real or a negative real, when you square it, you get a positive output. So everything is being colored by the output of this function, means that everything on the real axis is some shade of yellow. 0 squared, of course, is still 0. And in the imaginary direction, right, I squared is equal to -1. And so the color of -1 is there at I. Likewise, the color of -1 is there at minus I, because when you take minus I and square it, you also get -1. So you see this color wheel going around twice. Some things that I notice, the difference between raising to the first power and raising to the second power, is the darkness in the middle here gets broader, gets bigger, and the outside gets lighter. So this is x to the 1 power, here's x to the 2 power, here's x to the 3 power, here's x to the 4 power. And when you think about the shape of the different functions just as real variables, real functions, right? The quadratic is, or y equals x just passes right through the origin. The quadratic comes down and hangs out for a while at 0 and then goes back up again. The cubic really flattens out and then goes back up. Fourth degree comes down really flat. So that's what you're seeing here. That really flatness means that the function is very close to 0 for a long time. And actually, on the unit circle, when you raise a complex number that's unit 1 away from the origin. You raise it to whatever power, you're still going to be unit 1 away. So the unit circle is still all staying on the unit circle with those nice bright colors. But outside of the unit circle, raising to bigger powers gets things big fast. Inside the unit circle, raising to big power pulls it down to 0 fast. Okay. So let's go back to x squared here. And I want to do x squared minus 1. Now, what I see is I see a couple of black dots. These are the x-intercepts. Right? These are places, if it's black, it means the output of this function is 0. And so I have a black dot here at 1 and a black dot there at -1, which are the two x-intercepts of that function, x squared minus 1. I notice along the real axis, yellow out here, blue through the middle, yellow on the end. But think about what the graph of y equals x squared minus 1 would look like, right? This is the x-axis. It's a parabola that comes down and goes back up again, right? There'd be two intercepts and negative in the middle part and positive out on the ends. That's what I see, positive out on the ends and negative through the middle part. Okay. I also see that in the imaginary direction, it's all shades of blue, so it's headed in the negative real direction, and they're getting lighter blue, so it's getting further away. So it's like it's headed downhill in both directions here. Let's change this to an x squared plus 1. X squared plus 1, notice on the real, across the real axis, it's all shades of yellow. It doesn't hit the x-axis. It's a parabola, but it stays above the x-axis. The x-intercepts for this function are at I and minus I, and I see them right here, this black spot and this black spot on I and minus I. Notice in the imaginary direction, it's negative reals to 0, to positive reals, back to 0, down to negative reals. This is a parabola opening downward. And in the real direction, it's a parabola opening upward. So what I see here is a saddle. I see a saddle where this is going up, this is going down. And in fact, that's a really good way to visualize what the graph of a quadratic function is when you allow the variable to be a complex number rather than a real number. That the graph is a saddle. Other things. Let's change that to an x cubed. I see 3 intercepts. Right? One of the things that's really cool about this process, this coloring here, is that I can readily see intercepts. I can see them, in a nice picture. But I can see some theorems as well, like the theorem that says if you've got a polynomial with real coefficients, that the intercepts are always real or come in complex conjugate pairs. This one has 1 real and 2 complex conjugates. You can throw in any polynomial you want here. There's a, oops, that's not what I meant to do. I wanted that to be a 5. So there's a 5th degree polynomial. Let's make it a little more exciting polynomial. Let's throw in an x cubed there. This should have 5 intercepts. Oh, potentially, no, it should have 5 intercepts. I'm not seeing 5. Is that because, look, there's one up there and one down there. Yeah, so I hope I'm still recording. Anyway, there's all kinds of things we can do. One thing I also want to show is something like this. 1 divided by x is, well, for a real function, there's a vertical asymptote at 0. And I see that vertical asymptote as a white dot. I also see it very dark around the outsides. In fact, the further I zoom out, the darker it seems to get. That's because there's a horizontal asymptote of 0, that in any direction, as x gets big, this is headed to 0. I am going to try to zoom back in now here. There we go. Some functions have, asymptotes and intercepts. So for instance, if I throw an x minus 1 on, wait, what just happened there? X minus 1 in there. This one, there's a black spot there at 1, but there's still that white spot here. So I see a vertical asymptote at 0, and I see an intercept at 1. I also see that this looks very yellow. Again, I'm going to zoom out, and I see that as I zoom out, the whole thing is getting yellow. This is telling me that this function has a horizontal asymptote of 1. As you get far away from 0, the color is going to yellow, which is the color of 1. It's the horizontal asymptote of 1. There's some really weird things that we can see here, and let's just do one example. The function e to the x is interesting, because what I see is a horizontal asymptote of 0 off to the left, and then it gets really big on the right. But in the imaginary direction, what's happening is I see that color pattern, that color wheel just repeating itself as I go. But that makes some sense to me, because if you think of what does e to the I theta mean, it means cos theta plus I sine theta. And so even though the theta is increasing and changing, you're still staying on the unit circle. So the output of e to the x, when x is an imaginary number, is going to be some point on the unit circle. And it just repeats itself again and again and again, kind of like sine and cosine do. Now, I want to change this, though, from e to the x to e to the 1 divided by x. And what I have now is definitely something weird going on at the origin, because you can't, what's 1 divided by 0? This is an example of what's called an essential singular point. That at 0, there's something really weird going on. In fact, I see that it's very black over here, meaning I'm close to 0, where it's very white over here, meaning I'm very big, very large. And then I see these colors changing in here, meaning that you're kind of going in all sorts of different directions. And I can take the magnitude out of this and just look at the direction by dividing by the absolute value of this thing. So what I'm going to do is I'm going to take this and I'm going to divide it by the absolute value of whatever I have here, e raised to the 1 over x. And suddenly I have kind of craziness. I'm increasing the accuracy of the plot, which of course takes a little longer to plot. As I zoom in here, you can see that these colors are repeating over and over and over again, which means you're moving around and around and around that unit circle. And at any point, the thing is, this essential singularity at 0, the function gets close to every single, in any neighborhood you choose, the function gets close to every complex number there is. Right? It goes crazy at this asymptote. Anyway, I've used this notion of complex numbers and colors to do all kinds of different colorings of things over the years. And anyway, it really helps me visualize what's going on with complex functions.